بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Great to see you all. No grades, no attendance. So I hope you're all here on your own responsibility. Hopefully, in my opinion, that's the best way to really to learn. No pressure. Just so I hope you're here to hear something new, inshallah. So this mini course is only 3 lectures. It's only on one topic, on one paper that I'm going to be telling you about, and it's focusing on aerial physical interaction. So aerial physical interaction is a common, not a common, but I mean it's a new trend in aerial robotics, where drones are being used not only to fly and to capture data or to see and have cameras and have remote sensing, but also to interact physically with the environment. So it's extending drones from being just flying sensors to being flying manipulators, so that they can manipulate the environment and interact with it physically. And there's a lot of applications that could be done in this area. And the paper I'm going to be talking within this course about is this TRO paper that we published a couple of years ago. It's titled Energy-Aware Impedance Control of a Flying End-Effector in the Port-Hamiltonian Framework. Okay, so this is the title of the paper that we're going to be discussing in details, inshallah, throughout this mini course. There is only one question that we'll focus on in this paper and in this mini course, which is how would you, let's see, so how would you design a control algorithm that would enable a fully actuated multi-rotor aerial vehicle which is what we're going to be calling a flying end-effector. So this fully actuated hexarotor or this fully actuated multi-rotor aerial vehicle is simply just a flying end-effector that you can interact physically with the environment. How would you design a control algorithm that would enable this kind of robot to physically interact with an unknown environment in a stable and safe manner? So here, these are the 4 keywords that you should pay attention to. The first one is that this is about control. So we want to design a control algorithm in the end. The second one is that we want to deal with an environment that we don't know, which means that it's unknown to us. You cannot say that, for example, this environment has some inertia properties or it will move in a certain way. You cannot describe any model about it. So we don't know about the environment. We cannot model it. We can only model the robot side, but not the environment side. And we want to interact in a stable manner. So this is the standard way when you're doing any control algorithm. But what's new here is that we also want to have safety. And safety is not stability. Okay, one implies the other, but not the other way around. Okay, so if you have a safe controller, this means you are stable. But if you have a stable controller, it doesn't mean that you're going to have a safe operation when you're dealing with an unknown environment. So this is the keywords that we're going to be discussing, inshallah, in the 3 lectures. First one today, we're going to be talking about just foundations, just laying the groundwork and moving from aerial interaction to all of the preparation that we need to talk about geometric impedance control on SE3. So this will be the topic, what we're going to go dive into the next time, inshallah. And we're going to be looking at impedance control, but not only the standard impedance control. And we're going to be looking at doing impedance control with wrench regulation. Okay, so all of the keywords, if some of the keywords, they don't make sense to you, hopefully, inshallah, today they will be at the end of the lecture. So we want to do wrench regulation by doing variable stiffness control. And we'll see that there's a nice property about impedance control, which is called passivity. Once we have variable impedance control, we're going to be losing this passivity property. And we're going to be understanding next lecture, inshallah, why passivity is important and why we want to maintain it. And then in the 3rd lecture, we're going to be fix what we broke. Okay, so we're going to be fixing this loss of passivity using what we introduced as what's known as energy-aware control. And we're going to be using concepts like energy rounding and energy tanks and safety to contact loss situations. So all of these different terminology, all of these different ways of doing control or thinking about control is all related to having this safe interaction with an unknown environment. Today's lecture, inshallah, what you're going to be exposed to, and I'm saying what you're going to be exposed to because this is only a 1-hour lecture. I'm going to tell you about a number of things here and there. I forgot to mention something here is that, this is a course. So don't think I was just something to come and this is not relaxing stuff. It's not something that you come and relax in the morning. hearing about it. So you need to do some effort. The only commitment you need to give after the lecture or before every lecture is only 1 to 2 hours of study material. I already shared with you one video yesterday. If you did not watch it or if you did not see it before, you can watch it before the next lecture because it's important. And you're going to be having small sections of the paper to read. This is the only way you can maintain, attention throughout the whole mini course, inshallah. Today's lecture will be on 3 subtopics. The first one is how would we think about modeling this fully actuated multi-rotor aerial vehicle, so MAV. And the second question is, what is the geometric Port-Hamiltonian framework? So it was mentioned a lot that we want to do stuff using this framework, this way of working, this way of modeling and control. Then we want to do this geometric Port-Hamiltonian framework. And the last one is, how would we represent a rigid body dynamics in this framework? So these are the 3 topics that we're going to be discussing today. And let's just start immediately with how would you model, how would you mathematically write equations of motion that would represent a flying end effect, okay, which represents our robot that we're interested in designing a controller for. So today is only about modeling, and we're going to be preparing the groundwork for the control, which will be next time. So this is a problem, the statement of what we want to do for what do we mean by flying end effector. So our flying effector we're going to be talking about is a fully actuated multi-rotor aerial vehicle. Fully actuated means that you can move it in all 6 directions. So one rigid body floating in space, it has 6 degrees of freedom, 3 translational and 3 rotational. And you can consider this whole body, this whole robot, which has multiple, it has multiple propellers and they're moving and so on. You can consider it as one single rigid body that's connected to 6 tilted propellers, all via revolute joints, so they're all rotating by electric motors. So this is the situation that we have from a modeling perspective. When we come to control, we're not interested really in modeling or writing in mathematical equations all of the details of how this robot works. So we're not interested, for example, we usually neglect for control purposes the dynamics of all of the MAV's propellers. So for example, all of the electrical dynamics that will go on, all of the inertia of the propellers, all of the moving parts that we have inside, we just forget about all of this from a control perspective. And we consider the whole MAV as just a single rigid body. So if you want to have, if you're simulating this kind of model in MATLAB or in Simulink or in Gazebo or in IsaacSim or any tool, you would usually have inertia for the rotor, inertia for the body. You would have joints and motors and all of these details. So you would have a very detailed model, and you try to make it as detailed as possible so that you can get high fidelity responses in the simulation. However, from a control perspective, we just neglect about all of these dynamics, and we consider we have only one rigid body that's flying in the air. We assume that we can apply a full 6 degrees, we can control it in 6 degrees of freedom, so we can apply 3 torques and 3 forces to it. And our goal is we want to interact with an environment, and what we need to do is only design an interaction controller for it. Okay, so this is the abstraction of how we're going to be dealing with this MAV. This is a bunch of terminology that we're going to be using throughout this course. The first one is that we're going to be denoting the inertia reference frame. So we want to do rigid body dynamics, so we just need to put some reference frame and design this controller with respect to these reference frames. So first we have psi I, which is the inertial reference frame. We're going to have an psi B, which is a reference frame attached to the MAV center of mass and can be aligned anywhere, so it's arbitrarily aligned. You have also one extra frame, which is at the end effector. So it's at the tip of the MAV. So this is just a fully actuated hexarotor. So it's one drone that has propellers that are all, they're not variably tilted, they're all just fixed tilted. And we have just one arm extending from this drone that the drone can, push or grip stuff and interact with. So this would be the end effector. This is just the tip of the robot, and we assign also to it a reference frame. We call it psi E. The configuration of a rigid body. So the starting point of designing of writing the equation of motion for this system is that you think of the configuration. So the configuration will be the position of the origin of this B frame with respect to the inertial frame, and the rotation matrix, so RB with respect to I, it describes the orientation of this reference frame B also with respect to the inertial frame. Okay? So we have rotation and translation. So translation and rotation. And because things will be moving around, so we have rate of change of positions, or rate of change of velocity, rate of change of orientation, and rate of change of position. So this will lead us to velocity. So we have two types of velocity because the thing is moving in 6-dimension. So it's moving in 3D space. So we have a 3-dimensional linear velocity, so an x and y and z, depending on how you call the frame. And you have an angular velocity, which is 3 also rotations of this body. So in the end, we have these 6 numbers that would correspond to the velocity of the rigid body. And we have here more information, which represents the configuration. And there also has 6 degrees of freedom. If you're not aware of what SO3 is, so SO3 corresponds to the special orthogonal group. The way we're going to be writing orientation here is in a geometric way, which means that we're going to be designing, we're not going to be assuming I have angles. I'm not going to be talking, for example, about Euler angles or quaternions, or I'm not going to be choosing a specific parameterization of representing the orientation. We're going to be considering the orientation just as a 3x3 matrix. Okay? It's not any 3x3 matrix, so it has a specific structure, and this is the space where these rotation matrices live. Okay, so here we have 9 numbers that represent the orientation. Here we have 3 numbers that represent the position, and 3 for the position, and 3 for the linear velocity, and 3 for the angular velocity. Okay. The kinematic equation of this rigid body. So how does it evolve with time? Okay, we're going to be having differential equations to describe that. So we have kinematics and we have dynamics. So the kinematic equation is simply the rate of change of position is equal to velocity, both on the linear, both in translational and both in rotation. If you have the translational side, so the rate of change of this point of this origin of the B frame with respect to the I frame is given by this relation to the velocity, so to these 3 numbers that represent velocity. And we have the rate of change of the orientation is given by this equation. Whether if you're used to, for example, Euler angles, you're going to have another equation here that represents the rate of change of Euler angles and its relation to the angular velocity. If you use quaternions, you're going to have a rate of change of the quaternion degrees of freedom and rate in relation to the angular velocity. So no matter what orientation, no matter what specific parameterization you're comfortable with in dealing with rotations, you're going to always have a nonlinear equation here. And this is also, this coupling between the rotation and the translation also appears in the above side. Okay, so if we have something like this, that we have some nonlinearity, some inherent nonlinearity, in the configuration, you would definitely expect that the equations of motion would also be nonlinear. We also have these highly nonlinear equations that correspond to the rate of the rate of change of momentum. So J here corresponds to the moment of inertia of the body, so the rotational moment of inertia. M here corresponds to just the mass of the whole MAV. V, and if you multiply M by V dot, you get the rate of change of linear momentum. J multiplied by omega, you get the rate of change of angular momentum. And as you know from Newton's law, rate of change of momentum is simply equal to torques or forces. So depending on whether it's rotational or translational. So the above equation is simply the rate of change of angular momentum is equal to a bunch of stuff. This is nonlinear system, so we have this nonlinearity. We have what people call the gyroscopic torques. And then we have some control torques and some interaction torques that we can apply. Remember that we're not only going to do control. So usually if you're going to do control for a closed system that's, it's isolated from everything else around it, you don't consider we have any interaction. You just say, okay, I have some control inputs and I want to design a controller to control the system, to follow some particular path or to go to some set point and so on. But now what's different is that we're doing interaction. So we have these interaction torques and interaction forces. And these are not disturbances. This is a big difference between when you're doing interaction control and when you're doing stabilization control, or maybe a trajectory tracking, or you want to do disturbance rejection. These disturbances, we don't want to reject them. Otherwise, if we reject the disturbances, we're not interacting with the environment. We want to be able to control the system in the presence of these interaction forces. We don't want to neglect, we don't want to cancel them or neglect them. So we have in the first equation, we have control torques that we can control, that we can design a controller for. In the bottom equation, you have the rate of change of linear momentum is equal to what people call the Coriolis forces. And we have the gravity forces in the body frame. And we have the control forces, and we have the interaction forces as well. Any question at this point? Clear? Okay. The way we're going to be working, so there is this geometric way of dealing with rigid body dynamics. So a standard way that you might have been exposed to at any stage is separating rotation and translation, right? So we have configuration variables for the rotation, we have configuration variables for the translation, and I have a separate equation for the linear momentum and a separate equation, linear momentum and a separate equation for the angular momentum. However, there is this fancy way, okay, but it's not just fancy. It's not about just writing equations of motion in a different way. It's actually very powerful and has a lot of structure in it and a lot of benefits for control, that you can represent both the translation and rotation in the same way. And this is what's known as SE3. So I remember I said that translation is just 3 numbers in R3, while rotation is 6 numbers in SO3, the special orthogonal group. You can also deal with translation and rotation in the same way, both together with what's known as the special Euclidean group. Okay, so SE3, which involves the rotation and translation both together in some way, also with some coupling. And this is beyond the scope of it. This is just to identify, to expose you to this idea of modeling on SE3. The kinematic equation, instead of having this one, which is a separate rate of change of position is equal to velocity, we have the rate of change of this new variable, what we're going to be calling the pose. So pose is simply the combination of position and orientation, both at the same time. Okay. So it's given by this H matrix. Some people call it the homogeneous matrix or homogeneous transformation matrix. So the rate of change of this homogeneous transformation matrix is equal, very similar, you see, to this equation that had the H multiplied by some angular velocity. We have also here something multiplied by what was known as the generalized velocity. So since the pose was a combination of rotation and translation, that this generalized velocity is also a combination of the translation and rotation, and we call this a twist. Okay, so the generalized velocity is called the twist. And in the second equation, which is the dynamics, it's only one equation that represents both the linear momentum and angular momentum evolution at the same time. So you have the rate of change of this total generalized momentum is equal to, this is a equivalent term to the Coriolis forces and the gyroscopic torques, both in the same expression. And then you have the gravity wrenches. So this forces and torques together, so linear velocity and angular velocity, when you combine them together, we call them a twist. It's 6 numbers that represent the generalized velocity. And forces and torques, when you combine them together, you get 6 numbers that we call a wrench. So a wrench is simply a generalized forces acting on this system. So we have the control wrenches and we also have the interaction wrenches. So this is a different way of writing the equations of motion. It's completely equivalent to this one, whether you're separating rotation and translation. And these are already equivalent to whether you want to have rotation with quaternions or rotation with Euler angles. All of these equations are equivalent to one another. However, when you want to go to control and you want to use the properties of these equations, it makes a difference which one you're using, which representation you're using. And the one we're going to be using will be this geometric one. And this is the most general one. Okay. There is also one extra detail, is that the equations of motion that you're used to, okay, which is separating rotation and translation, they only hold if you assume that you have the reference frame at the center of mass. If you have shifted from the center of mass in any place that's still fixed within the body, these are the general equations that correspond to that, and you get extra terms in the other one. Okay, so these are really the most general form and applicable to any scenario. So this was just an introduction for those of you who had the geometric control course. This is just a refresher. For those of you who have never heard this stuff before, this is only to highlight some keywords that we're going to be dealing with. It all boils down to pose, twist, which is generalized velocity, and wrench, which is generalized force. So this is the only things you need to know. You need to know that the equations of motion you might have seen in other contexts, they look differently here, but they correspond to the same thing, which is the rate of change of momentum is equal to applied wrenches on the body, which is simply Newton's law. So now let's look at the geometric Port-Hamiltonian frame. So this is the part that I think it's new for everyone here. This is just a general introduction about what is this framework, where does it come from, what are we trying to do in it, what's this way of thinking. So when I say a framework, it's more of a way of thinking. Okay? It's not like a control technique that you learn and you can do with it stuff. It's more of a way of thinking. You have to really shift your way of thinking from the standard way of looking at equations of motion and thinking about controllers and trying to design and tune these controllers and extend them and do stuff with them in applications, to this consistent framework that has 3 roots in different fields. So the first root of this geometric Port-Hamiltonian framework is what's known as port-based modeling. So port-based modeling is So port-based modeling was previously, okay, it's still now called by some people by bond graphs. So it's more famous actually in terms of bond graphs. And it was introduced by an MIT professor I think in the 60s. It's called Henry Painter. And he proposed this idea that when you're dealing with systems, when you're thinking about representing it visually and you want to connect one system to the other and you have interaction between them, this interaction is never one way. So you never say, so you're all used to the block diagram, right? So you have this block diagram of the plant and you have a controller that applies a signal to it. And then you take one signal from this plant and you feed it back to some comparator and you produce a signal again to the error and so, to the error signal to the controller and so on. This, nice way of thinking about systems only with signals, it doesn't hold in practice, actually. It holds in practice, but there's a better way of thinking about it, okay? There is always interaction bidirectional when you have systems. You always have one subsystem connected to another one using bilateral signals, okay? So there are always 2 of them. And in this notation, he called them effort and flow. You always have this pair of variables that correspond to, together, they make up power. Okay, so together you can talk about, instead of having one signal from moving from one system to the other, you always have power exchange between 2 subsystems. You have energy exchange between one system and the other. So you always talk about energy as the core principle, as the core concept in bond graphs or in port-based modeling. So, and he just introduced, instead of just writing arrows all over the place, he introduced this combined, okay, notation for these 2 arrows and called this a port. So the pair of an effort and a flow variable, they are usually called a port, or in the old notation, it's called a bond. So both of them together, they would correspond to power exchange between one subsystem to the other. So when you're thinking about a robot, you usually have multiple subsystems in it, not from a functional perspective, from an energetic perspective, and this will be clear later, inshallah. You have multiple subsystems that they are interacting with each other through effort and flow variables. If you have the robot as a whole interacting with the environment, you also have effort and flow variables between the robot as a whole and the environment through effort and flow variables. This powerful way of describing systems was actually very successful in trying to unify a lot of multi-physical domains, not just about, this is not just about robotics. This is applicable to multiple physical domains. I'm going to show you in a bit some examples. The second root of the geometric Port-Hamiltonian framework is what's known as geometric mechanics. So geometric mechanics is a field by itself. It's a field of applied mathematics where, you're all familiar with this equation, right? So this is x dot equal to f of x and u equation, which is in control, this is, our bread and butter. We always try to represent any system that's moving in the real world just by a bunch of equations that look like this. If you have never been exposed to nonlinear systems, you're familiar with the equivalent linear one, which is the x dot equal to ax plus bu, y equals cx version of it. Okay, but this is just a generalization to nonlinear systems. So the geometric mechanics people, when they think about systems, they usually try to write coordinate-free descriptions. Once you say I have an x, you've already chosen coordinates. You've already said that I have x1 and 2 and 3 and so on. You start to write them, in components, and you have the equations. They look ugly, but they are very comfortable because you see everything that's happening. So in geometric mechanics, you try to abstract all of these coordinates because the coordinates is a choice, and the equations of motion, they should not depend on the coordinates. As an example of what I just said, what I told you earlier about, for example, rotation matrices, this was a choice. I can represent orientation by rotation matrices, by quaternions, or by Euler angles. Any result I get from any one of these choices should be applicable to all of the 3. Right? So it should not, the evolution of the system should not depend on my choice of coordinates. The same also for x and y and z. You're all familiar, you're all comfortable with putting a frame and saying I have x and y and z. Why don't you use polar coordinates or Cartesian or spherical coordinates or cylindrical coordinates and so on? any result you get should be applicable in all of these frames. So this is the idea of coordinate-free descriptions. And this is where the theory of manifolds and differential geometry is used a lot in geometric mechanics, trying to abstract all of these concepts instead of looking in terms of coordinates, trying to understand really the geometric picture in a independent of these coordinates. This was very successfully applied to both finite dimensional systems and also infinite dimensional systems. So most of you have been exposed to finite dimensional systems, which is by differential equations, ordinary differential equations. However, there are also a lot of interest in designing controllers and modeling systems which have partial differential equations. Okay? So for example, there's a whole field called soft robotics, where we have these soft, because of the stiffness and compliance in the robots themselves, you already need to describe them with infinite dimensional systems, which are partial differential equations. The whole idea is that when you're describing in the geometric mechanics, in this way of describing systems, you have this idea of a state space that has a manifold structure, and this is applicable to many examples. And you can abstract. You can really see that there's a lot of similarity between, for example, rigid body rotation and rigid body motion in general. You can talk about fluid flow, for example, Navier-Stokes equation, or nonlinear elasticity. You can go to more complicated partial differential equations. Okay. And the third one is systems and control theory. So systems and control theory is in the end, when you're all familiar with this, you know what systems and control is. But when you combine these two approaches with systems and control theory, what you get is that you get a powerful way of describing the system at the modeling level, and then you can exploit this to do energy-based analysis and control. So this is the whole idea. So when you have all of the three elements together, instead of working with this standard way of modeling systems, the standard equations of motion, you look at it differently. You start to see it in this way where you look at more, the f of x has more structure. Okay, this will not make sense to you. Maybe hopefully by the end of this lecture or maybe the next one, this will make a little bit more sense. That the only thing I want to emphasize is there you have here this extra structure. You have more stuff into the f. It's not just one big f, and then it's like all of the equations you cannot differentiate what is this one doing and what is this term. You really have a lot of structure within this f of x. And the g of x and the h of x, you also can choose them wisely in a way that would represent the input and output, the really input-output behavior with respect to energy. And so you're all familiar with this block diagram way. So this is just representing these equations these are all internal. There's no control here yet. So this is simply you have the control that you need to design. So we're only talking about the modeling of the system. So you see we're adding more structure instead of just saying we have one big f of x. And with the Port-Hamiltonian framework, you start to give all of these elements more meaning. Okay? So they tell you more about the system. You start to see that there are some elements in any dynamical system, and this is really the most powerful thing about Port-Hamiltonian theory, is that this is applicable for any dynamical system. You can always find a way to write it like this. So for any dynamical system, you'll always find there is some stuff related to energy storage, some stuff related to energy dissipation, and some stuff inside, and some stuff that, these are the energy supply, these two signals, that I'm going to be connecting to the controller or connecting to the environment and so on. And there is always a lot of complicated stuff. There's a lot of nonlinear terms, and they make our life miserable. But once you look at the true role together, and you really see that this is just an interconnection structure. This is what in the Port-Hamiltonian literature we call as a Dirac structure. So in this Dirac structure, we simply have all of the stuff that are neither related to energy storage, nor energy dissipation, nor energy supply. You just have routing. It's just an interconnection of stuff. This doesn't make sense, at the moment. Hopefully in this lecture, we're going to be seeing an example of something you should be familiar with in modeling and how it would look like in the Port-Hamiltonian framework. So just a quick, let's go a little bit back, just to look a little bit of some basics of this port-based paradigm. So the most important concept, physical concept in physics is energy. You've heard about energy so many times. You heard about kinetic energy, about potential energy, about magnetic energy, about electrical energy, there's so many forms of energy. And when you go to thermodynamics, you have entropy and you have the Gibbs energy. You just have a bunch of all of these stuff. So you've heard about energy a lot, but you never use it. That's the thing. So when we're doing modeling and control, energy is like, it doesn't exist. You never see it. It's something, on the side. And you already know if you took any course on, for example, on linear control, one very powerful way of designing controllers is using what's known as, or designing, assessing the stability of dynamical systems is what's known as Lyapunov theory, exactly. And you use in Lyapunov theory something that looks like energy, it acts like energy, it's a scalar function, you want to see it decaying and so on. So you see, we need to have this concept of an energy function that represents the evolution of the system. So there are a bunch of stuff they know about energy and how important it is. I'm going to be skipping that. What I want to emphasize here is that any two subsystems that you have, any two dynamical subsystems that are interacting with each other, they are always interacting by some flow of energy. In the Port-Hamiltonian framework, you describe this energy flow between these two subsystems by this effort and flow variables. The effort and flow variables, they live in two complementary spaces, in some sense. And you can always take the pairing between them. Okay, you can always combine them and get one number in the end. Okay? So you can always take the effort variable, combine it with the flow variable, and in the end you should get some units of power. Okay, this power can be mechanical, can be electrical, can be magnetic, and so on. So you can be generic, and then you can always have from moving from one physical domain to the other, because this energy is a concept that's not depending to some physical domain on its own. And one half arrow that looks like this, which is what we call a port, is simply two arrows. It's either one system supplies the effort and the other supplies the flow, or the other way around. The first one supplies the effort and the other one supplies the flow. You always have this bidirectional case. And if you take this concept and you apply it to different physical domains, you're going to be seeing we do have all of these pair of variables. For example, in the translation, when you talk about translational mechanics, which is just simply one point mass that's moving in space, you have forces applied, which are like effort variable, and you have flow variable, which is the velocity of this point mass. What is the product of force and velocity? Mechanical power. If you have something that's rotating, you have some torques and angular velocity. What happens when you multiply torque and angular velocity? You get also power. Rotational power, right? So mechanical power, but it's rotational. When you combine rigid body mechanics, which is this dealing with one system, both with rotational and the translational side at the same time, you get what's known as the wrench, which is equivalent to the force and torques, and you get the twist. And if you combine the wrench and the twist, what do you get? You get also the sum of the rotational power plus the translational power. Okay, so you see it's very easy that you get it's just a sum of the two powers that was on the top. Electromagnetism have the same. You have voltage and current. You all know that the multiplication of voltage and current is also power. Hydraulic case, when you have pressure and flow rate. Okay, if you took any fluid mechanics course, you're going to be seeing there was always this combination of pressure and Q, okay, which is also hydraulic power. Thermal domain, you also have a combination of temperature and entropy flow. And even in chemical systems, okay, if you have dynamical systems that represent some chemical reaction, you can also have chemical potential and molar flows. Okay, if you already know what that is. So you see this idea of really having effort and flow variables and describing system. Yes.
Then like the input and output, like force is the input. We said just say for output is just the velocity.
If you say you already have an input, you've already decided what the causality of the system is. But this is not usually the case. I'll give you a small example. So this rigid body, when it moves, do you apply on it forces or not? You consider forces to be the input, right? What about now? I'm already moving it. Can you say from a conceptual point of view, the velocity is the input and the forces are the output? It's the same, right? So this is just a causality issue. Whether there is something that's naturally as an input or naturally as an output, it depends on the physical example. Okay, if you start to think about it, properly, you're going to be seeing that there are some problems that have as an input naturally a force, and some other problems they have as an input naturally the velocity. For example, a spring, right? When you have a spring, you compress it, and then as a result, what do you get as an output? The reaction force. So you see the force for the spring is actually not an input, is an output. Yes.
In the system we're talking about, usually we use because energy is like different forms. Do we include sometimes voltage and current, for example, for motors or for anything in the final system?
If you do have that, in this, usually we do it, if I go back, to remember this assumption, I said that. In the simulation wise, if you really want to have a high fidelity simulation, we do have a representation of the voltage and the current, not really in terms of, in terms of microseconds, because these are very fast dynamics. If you have a very fast dynamics in a simulation, this means that you need to have very small sampling period, which means that the simulation will take forever. So usually what happens is that you try to neglect all of these fast dynamics and maybe put like a closed form model for it. You say that I have maybe a first order equation that represents all of the motor dynamics, something like this. Usually this is how we do. This is, for example, how Gazebo does it when it tries to simulate any robot and so on. So you can have the actuator there, but not in terms of voltages and current and temperature, and start to go to Maxwell equation and have electromagnetism flowing. It's not that detailed. Okay. So a physical system. So how do we do? So these are just building blocks. So we just said that okay, these are just one effort and one flow variable between any two subsystems. But how do we talk about storage of energy? So any physical system that you have, you're gonna always find that it has some sort of energy being stored into. You're not thinking about it explicitly, but it's always there. So any interconnected physical subsystem can be seen as a set of different subsystems interacting with each other. For example, a mass spring damper system, what does it consist of? A mass interacting with the spring, interacting with a damper, right? So you have three things. An RLC circuit, is it composed of? A resistive part interacting with a capacitive part that stores electrical energy, and an inductive part that stores magnetic energy. So each ith subsystem, you're going to find you always have some sort of state or an energy variable. You also have an energy function that corresponds to the stored energy. You have a flow variable and you have an effort variable that will tell us how the rate of change of this stored energy is. Okay? So what is the rate of change of this stored energy? So this is very abstract. An example of this is simply a point mass moving in 3D. So a point mass moving in 3D, the state of it is momentum, okay? Or equivalently velocity. You can always choose as velocity and you choose as momentum. Momentum is the correct way of thinking about of mechanical systems, really, to say that this is the state, okay, for reasons I'm not going to be discussing about here. So we can choose the momentum to be the state, and then you're going to find that the kinetic energy is usually what's stored in this point mass. It's moving around, and you all know, okay, from basic physics that I can always say that this moving mass that has some forces applied on it, and it's moving and has some velocity, I can always invent something called kinetic energy. What is kinetic energy? It's no new information. It's simply just half mv squared. Or if v is three-dimensional, it's half mv transpose v. Or if you write it in terms of the momentum, which is equal to mv, you can simply write it as 1/2m p transpose p. Same, you see, there's no new information. It's a made-up concept. Energy is just a made-up concept that helps us analyze systems. Flow, which is the rate of change of momentum here, is simply the rate of change, so p dot. And the effort variable is the gradient of this kinetic energy. If you take this equation, take the gradient of it, you're going to be seeing that I have the gradient is P over M. What is P over M? If P is equal to mv, what is P over M? Simply the velocity. So the effort variable here is the velocity. Now if you look at what is the rate of change of kinetic energy for this point mass, it's simply equal to velocity transpose P dot. Usually you know that P dot is equal from Newton's law. The rate of change of momentum is equal to what? Applied forces on the system. So you see here we have a force-like variable, which is the flow, and we have an effort-like variable, which is the velocity. Here, the effort and the flow variables, they can always shift. You can always, and this is the point that Muhammad made. So you can always have the flow as an input or the effort as an input and so on. It doesn't matter really. And this is why it's so in the old literature of bond graphs, they usually had this convention of saying that flow is always a velocity and effort is always a flow. But in the Port-Hamiltonian framework, we usually don't make this distinction. We say, okay, the effort is simply the gradient of the energy the energy function with respect to the state variable, and the flow is simply the rate of change of this state of this energy variable. Yes.
So based on what you just said now, we can make some choice of some of this, for example, the state, such that we get the roles to be reversed.
Yes, exactly.
The force and the flow.
Absolutely, exactly. This will exactly happen if you choose V. So if you choose V, No. In this case, no. But usually, if you look at a spring, okay, a 3D spring, you're going to find that actually the force, what is force, becomes a flow. The force becomes an effort, and the velocity, like variable, becomes a flow. This usually happens for springs. It depends on the system exactly. That's why. So in the standard bond graphs, they have they have this distinction between the systems that have naturally a flow to be velocity and a naturally a flow effort to be naturally a flow to be force. But here we don't make a distinction. We make it in terms of the state variable itself. So you see all of the individual subsystems that you have, you can always think about that it has some stored energy. You can also have no stored energy. You can have just dissipation of energy. What is something that you, for example, in mechanics that has dissipation of energy that you can think about? A damper. What else? Sorry? Friction, exactly. Also friction has, a dissipation of energy. So you see friction and damping, okay, they're not, okay, so they're not storing energy, they're just dissipating energy. Yep. A resistor would be in the electrical part. Yes, exactly. You can have an electrical resistor. This would correspond to the dissipation there. Exactly. In magnetics, you have also the same and so on. So we have this, you can extend it to the other domains. And once you have now all of these, individual subsystems, what you're going to be doing is simply, you're going to be combining them using ports. So the whole idea of the Port-Hamiltonian framework is that instead of looking at the equations of motion, just, all blended together, this big f of x that, everything is merged together and entangled with each other, can you just decompose it? Can you write it in a way that we have all of these different parts and they are interconnecting using power ports? And in the end, the total energy would be simply just the sum of the individual energies, just like, with the wrenches and twists, it's equal to the sum of the rotational part of the rotational energy and the sum of the translational energy, just the sum. And in the end, you can write the equations of motion in this generic way, which is, in this generic way, which is the Port-Hamiltonian way. You have the x of dot is equal to j of x minus r of x. So you have something related to j of x here would be the interconnection structure, stuff that they don't affect the energy flow. They don't affect the energy, neither in a good way or in a bad way. They don't store it. They don't dissipate it. They're just, okay, they're just nonlinear terms that you have in the system. R of x is related to the dissipation part. And then you have the gradient of h with respect to x. This is the choice that we made. We had the variables x and dot and partial h by partial x. These are the key choices that we made to rewrite the equations of motion. And then you have g with the input, and you have y, which is g transpose multiplied by the gradient of h with respect to x. So this is the way, if you have a model like this, we call this the Port-Hamiltonian model or representation of a dynamical system. And now if you compare it to the standard state space representation you're used to, you see there's a lot of structure. There's a lot of stuff I can use. The J, because it's actually something related to energy, okay, routing, it's not changing the energy, has a very important property. It's skew-symmetric. And you're going to be seeing why this is very important for control purposes later on. The R of X is semi-positive definite. Okay, so it's something because energy is always dissipated out of the system. You cannot have negative dissipation. You cannot have this, energy flowing to the damper. The damper always takes energy and flows it outside. This is why the R is always positive definite, in that sense, semi-positive definite. And the G, you see here, we have the G and the G transpose because they have what's known as collocated inputs and outputs. You think about the inputs and the outputs that make up energy together, okay, such that you can talk about power coming through the system through an external place. Yes, ma'am. Yes, exactly. Exactly. It will definitely be used in stability. Yes, absolutely. Rx is the only thing that will make a system, asymptotically stable, that it will really dissipate all of the energy and then stop eventually in the end. Okay, but going from this is only passivity. Going from passivity to stability is an extra step. So it will tell us about the passivity of the system. The J of X tells us nothing about the stability because it's just skew-symmetric. You're going to be seeing whenever we have any Lyapunov analysis, the J of X will disappear. And this is the most important part, the most important technical advantage we get. when we're writing equations of motion and we're doing stability, things become, you know, you're not gonna really believe how easy it becomes to do just stability analysis. It becomes just a one-liner because all of the nonlinear terms. If you ever did Lyapunov analysis at one point in your time, you're gonna be seeing there's a lot of terms, you know, just cancel this one with that one, this one with that one. All of the things that cancel out is simply skew symmetric in nature. This is what makes up the skew symmetric part. Yes. J, this represents the interconnection structure. R, it represents the dissipation structure that we have. The G represents how the input, how the external port to the system, how is it interacting with this system. Okay, so you see the external part is usually we don't know about it, but we only know how it enters the system. Okay, so this is what the G part tells us. Okay, and usually here, so this is just a simplification. You can also generalize this. The G itself, you can also write it as a function of X. You can have this generalized way. So also the input can come into a nonlinear fashion. Okay, it can be multiplied. It can be in a fine manner. Okay, it can be multiplied by a function of X entering the system in general. Okay, many questions I think. Previous slide. This one. This one. Yeah. Yes. We don't usually choose. So velocity and force, they're going to always be effort and flow. When we choose the state, we're going to usually use either configuration or momentum. This is for mechanical systems. It depends. This is just a convention. This is just a convention usually. Okay. You see that momentum and velocity are always related to each other. So momentum is no extra information, you know, it's just velocity multiplied by the inertia. The momentum becomes much more powerful in analysis and doing control if you have something that the inertia is not fixed, is not constant. Then momentum becomes really different. You see that, for example, in the standard manipulator equations. For example, m of q multiplied by q dot. So q dot is the velocity there. M of q is not constant. So when if you introduce a new momentum variable, you call it m of q multiplied by q dot, the rate of change of this momentum variable is not equal to mv dot or mq double dot. It's actually some extra stuff. Okay, we can discuss this later. Yes.
So, with respect to
Next slide. This one.
No, okay.
This one.
So can we easily move from the standard state space representation, because now that's what we know as the representation for whatever control,
yeah,
to the Port-Hamiltonian representation?
The answer is no. It should, you should, but usually not. I'll give you a simple logical answer. Okay, if I give you a mixed juice, can you unmix it? No. Can you say, okay, this is a half banana, half strawberry? I don't know, with others, you cannot. But if I give you banana and strawberry, separately structured, you can also make them blended, and you know you can go back and forth. So if you know, usually, and this is a philosophical way of, this is just a philosophical answer. Okay, in principle, you should be able. Okay, if you already know how the Port-Hamiltonian system would look like, you can always take this and make it into that. But usually, what happens is that we have extra stuff here that sometimes are zero. Sometimes they cancel out with each other when you go from this to this expression. So you cannot say if I tell you there's a zero term here, what was it? You know, what did it come from? You cannot say that. This is the technical reason why.
And without following this particular convention, of course, this is the convention for Port-Hamiltonian system. But can we then from a particular mechanical system or whatever system, can we write a set of equations from first principles and get this?
Absolutely, yes. Excellent question. So the question was, can we, from first principles, you know, just follow simply, you know, Hamilton's variational principles or Lagrangian way of thinking about stuff? Can we just follow a bunch of rules and in the end we get the equations of motion? The answer is yes. And the surprising, you know, answer is that usually it comes more naturally in the Port-Hamiltonian, and then you start, you know, to remove all of this stuff. So actually, this is related to Hamiltonian mechanics and Lagrangian mechanics. Usually, most people in robotics they're more exposed to Lagrangian mechanics, which is, for example, in manipulators, the M of Q double dot plus C of Q dot equal to some torques. This is the Lagrangian way of looking at systems, but the equivalent Hamiltonian way, okay, it's also equivalent, and you can also derive it, but it's less popular, okay? But more powerful, more, and this is just, you know, it depends on who you're talking to, but in my opinion, it's more powerful. Okay. Yes. Yes. It must be. That's the thing. It's because it's the same system.
J can control what we represent our
the J of X, the G itself. Yeah, the G in both. So G here. So the U and the Y, they're always the same. You see here, the U and the Y, they're usually the same in both cases because these are like the inputs and the outputs. Okay, so usually they're going to be appearing the same, you know, same thing. The choice of X is what makes things different. So if you have the X, you know, so for example, you choose X, you're going to get different equation here. I'll give you even a small an equivalent example. You know, if you take a two-link robot arm, okay, you can always say that I have M of Q double dot, and so on, the rest of the equation. What is the Q? For example, if you have a two-link robot arm, do you choose the angles between one joint, so one frame and the other, so the two relative angles, or do you use the two absolute angles? Depending on this choice, you're going to get a different mass matrix and different C matrix and so on. So that the equations of motion, they look the same. You have the same torque inputs in the end, but the choice of state makes the equations look differently. Okay? So state space representation is always the first thing you should have been told when you took any state space representation, is that it's not unique. I can always shift it from one way to the other, and you always write it in a different way depending on the purpose. Whether you want to do analysis, for example, if you have the linear case, x dot is equal to ax. You want to do analysis, you do maybe, for example, a polar decomposition. You look at the eigenvalues and eigenvectors and so on. If you want to do control, you put it in a controllable form. If you want to do observer design, put it in an observable form, and so on and so forth. So there are just different states that will give you different representations. So let's look at the Port-Hamiltonian model of the point mass. So this is a very simple equation. It's simply m x double dot is equal to gravity forces plus some control forces. Okay, so the standard equation. There's no damping, no stiffness, just a mass. There is a gravity. So you just, you know, if you have a simulation, you just simulate it, it falls down. That's it. Okay, and you have some control force that you can make this, you know, point mass do something similar, something interesting. So the equation of motion simply is you have kinematics. So psi dot, psi is here the position, okay, with respect to some reference frame that you choose, is equal to the velocity. And mv dot is equal to gravity forces. So mg in the direction of, okay, of the z. For example, if you say that the gravity is downward, and you have the control forces. Easy. Okay. To write it in a Port-Hamiltonian way, so will take us a whole lecture, you know, or maybe 2 or 3 lectures just to tell you the proper way of deriving Port-Hamiltonian. I'm just going to be, you know, doing mathematical manipulation just to show you that it could be written in this way. But I'm not going to be deriving it from first principles. So a point mass has 2 types of energy. So whenever you're talking about systems, you stop here, right? You have an equation and you're done, right? So you don't think about the energy. But a point mass moving in 3D has kinetic energy plus gravitational potential energy, right? mgh, right? So it's just height, which is here the z component of the psi, okay, which is simply multiplied by mg. What is the gradient of this Hamiltonian with respect to the 2 states? What are the states here? We're going to be choosing configuration, which is psi here, and not velocity, but the momentum. So configuration and momentum, this is the choice, usually the choice of states for any mechanical system, configuration and momentum. So the rate of change of the configuration, so the configuration is our first state, and the momentum is our second state. So yes. No, by configuration, I mean either position, orientation, or pose for a mechanical system. Or if you have a 2-link or n-link robot arm, it would be the joint angles. joint displacement, and so on, okay? If you have a floating base manipulator, it would be the configuration of the base and also the configuration, the angles of all of the robot, the manipulator arm. So the gradient of H with respect to psi is simply equal to mg, okay, in the z direction. This is just, I have an mg, which is just in a number, like a mass times 9.81, but we need to make it into a vector. So we have a direction of z, it's positive. And then we have the gradient of this kinetic energy is equal to P over M, which, as you said, okay, so earlier, it's the velocity. Okay, so we have here so what is the state? Okay, it's configuration, which is the position and momentum. What are the gradient of H with respect of the kinetic energy, of the total energy of the system with respect to these two states? I have mg in a direction, and I have velocity. Can we rewrite these equations using this information? The answer is yes, and they look like this. Take a moment to see whether this is really the original system we had or not. So psi and p are the two states. So these are two x's. So x dot, which is psi dot and p dot, is equal to something, okay, as a function, so it's a matrix that's going to be multiplied by partial h by partial psi and partial h by partial p. We said that, so this is equal to 1 multiplied by partial h by partial p. Why is that? Because psi dot is equal to v, and v is equal to p over m, and p over m is equal to partial h over by partial p. Make sense? What about the first one? Why is p dot is equal to minus this term? What does this represent to you? What is this term? First of all, what is p dot equal to? P dot is equal to forces. All of the forces applied on the body. How many forces do we have here? 2. We have one due to gravity and one due to the control. The one due to the gravity, where does it appear? It is mg in a direction. It's minus mg. If the gradient of h with respect to the psi is equal to mg up, then the gravity is minus mg up. It's mg down. This is the minus sign. Gravity force. Okay. And this is something by the way, this is not something, it's something you knew. You've always heard about this. You always know that potential energy, a potential force is a force that comes as a gradient of potential energy. I'm pretty sure you've heard this before. Maybe in the context of a spring, you've always heard that the spring force is equal to the gradient of the spring potential with respect to the delta x. The same also for gravitational potential energy. The gravity, you can think of it as the gradient of some potential energy. We call it, which is mgh, and so on. But you can generalize this concept to more complicated cases. So this is the first term. And then we have, there's only one last part, which is Fc, which is the control force. It entered in the second equation only because of the dynamics. We have the momentum balance. And then as an output, so this is something that's new. You see, whenever you're working here with this equation, you just think about two equations and new output. But when we write a Port-Hamiltonian model, you always need to think about what is the output that is conjugate to this force, to this input. So this is the equation of motion. You see, what we simply did is that this was the g, then we wrote it. So now we can write it just in compact form. You have something looks like this. So x dot is equal to j. J here is constant. It's not a function of x. It could be in general. Here is just a constant multiplied by partial h by partial x plus the g multiplied by the input u. And then you have the output y is equal to g transpose partial h by partial x. Okay. So this is an extra equation. It's just redundant. Just an output equation. It's not saying anything new. But it's very important because it identifies what is the conjugate variable with respect to v. You see, you have a flow variable and an effort variable. Right? Or a force variable and a velocity variable, if you want. It's very important that this is skew symmetric. Okay, we're going to be seeing why this is important next time, inshallah. And in the end, a point mass, you can think about in terms of two things, only two things. It is storage of kinetic energy. That's it. and some external power coming from outside. And everything else, the J and the G, they don't matter because they just tell us one thing, which is something you all know for a point mass, that the rate of change of kinetic energy is equal to the power supplied through control. That's it. This is exactly what this bond graph tells us. So this is what's known as a bond graph. What we described, we simply rewrote instead of thinking, about a force. This is not a block diagram. This is completely different from a block diagram point of view. A block diagram simply would say that I apply a force to the point mass, it moves the negative velocity, right? And you write them, force in block diagram, force velocity out. But this is different. See, first of all, the point mass itself, I decomposed it into a G, and the storage of kinetic energy. Sorry, storage of total energy of kinetic and gravitational potential energy. And then the input and the output, I put them together into some port that describes the power supplied to the system. Now, question to you, how hard is it to do this for the UAV? For a floating based, for a flying end effector, for something that's rigid body and 6-dimension, and rotation and translation, Yes.
It's understood how you have the FCP and the JG.
Okay.
Getting that to the storage, how do we get these parameters?
I'm going to tell you more later, inshallah. Just let's keep it like this for now. Okay. I'm going to tell you more details about this, inshallah, next time. Okay. Yes. Yes. No. Have you ever seen, just a small example, have you ever seen when doing any analysis, torque multiplied by theta? If you can find it, I'll give you a big prize. Never. It's impossible. You always find when doing analysis, torque multiplied by theta dot. You always have this combination. Why? Because these are the power. You never see torque multiplied by theta. You never see position multiplied by force. You never see this combination. So position is always a state. It appears as a state. This is the position. Okay? While velocity always as an input or an output. And force is always input and output depending on the system you're talking at. And momentum is the other state conjugate to position. This is very generic to mechanic systems. Yes. Sorry? Why? Sorry? Is work equal to power? That's the thing. You can talk, so power, so what you just said is that work depends, so first of all, work is equivalent to energy. That's why when you always talk about the rate of change of work. You don't talk about work itself. You always talk about the rate of change of work is equal to something. And then you rate it to the rate of change of energy. Okay? And there's another thing, that the work itself is something you all know about. For example, the work depends on the path you took. But power does not. So power is something, as a time, it has only time dependence, not path dependence. This is again related to this concept. Okay? No. Okay. So for a floating based manipulator, for a fully actuated hexarotor or a flying end effector or just an MAV, this is the equivalent Port-Hamiltonian model. Doesn't make any sense to you. Okay. Hopefully, inshallah, when you're studying in the weekend, it will make. Okay. So this is your homework, trying to prove that this is really what you had earlier. Okay. So first of all, what is our two states? We have pose instead of position, which is the H, and we have generalized momentum instead of the linear momentum. So do you see any analogy? Clear. You have something that looks very complicated. It's no longer just 0, 1, and -1 and 0. It's not just constant. It's also depending on the state, which depends. It's depending on the momentum, and it's also depending on the H. So it's very nonlinear term. But it's skew symmetric. This is very important. This is a very fully skew symmetric, operator here, multiplied by the gradient of H with respect to the first state, the gradient of H with respect to the second state. So the gradient of H with respect to pose, and the gradient of H with respect to momentum. Forget about the gradient of H with respect to pose part. What do you think the gradient of the kinetic energy with respect to the momentum is? Sorry? The twist, exactly. Just like when we had earlier, the gradient of H with respect to linear momentum equal to linear velocity. the gradient of kinetic energy, the general one, with respect to the generalized velocity, the generalized momentum, will be equal to the generalized velocity, which is the twist. So this is also analogous. This part will be very nasty. I'm not going to be talking about at all, okay? Because this is the gradient of a function with respect to a matrix. Yeah. Out of the scope, the guys who took the geometric control course, I'm pretty sure they heard about it, but they don't remember it now. Okay, and then yes, those that took the course. So, and then you have the input, which are simply the wrenches due to control and the wrenches due to interaction. What is the energy of an aerial robot? Okay, if you forget about all of the, all of the actuator dynamics and everything, you just have kinetic energy. It looks like this. It's very similar to half 2 over m, okay, P transpose P, but the P now is 6-dimensional. The I itself, the I inverse is instead of the m, was instead of 1 over m. Okay, so the I here is the generalized inertia. Okay. And then this is the potential energy part, which is exactly the same as m, g, okay, h. Okay. But you need to take into account, that you have 3 dimensions. Now you're moving in 3 dimensions. Yes.
What is X?
Psi. So this one. This is the function. It's a function that will take the twist and give you h dot. Have you seen something like this before? So some function that takes a twist. This is this twist. So this is a function that maps the twist and tells you what the h dot is. And this is the dual map that will correspond, that will give you a wrench if you tell it what the gradient of h with respect to, if you tell it what the gradient of some potential function with respect to the pose is. So we spent 3 lectures trying to tell you what this part is, if you remember. Sorry? It's related to the adjoint. It includes also the adjoint in it. Okay? But there are more details here, more technical details. The bottom line is that, okay, so that's the end, the last part. So the bottom line is that it could be written in the Port-Hamiltonian. That's the first, okay, thing. The second thing is that it's very analogous to the point mass. So if you're doing control for a point mass and thinking about it in a Port-Hamiltonian way, it becomes as easy, okay, from at least, with respect to the parts that are similar, to doing it for a full rigid body. Okay? Yes. So I'll take a couple of questions, okay, and then we can stop. Okay? Only 5 minutes for questions. Okay. So
here because now as an assignment we want to prove that this naturally leads to this.
Yes.
Taking the partial with respect to that's the lead derivative stuff, right?
I'll answer this question in the end. Let's take easier questions first. Yes, question? Yeah.
As the system is fully actuated, we don't need the nested control loop, right?
That's right.
Because the orientation and position is decoupled.
Exactly.
This is the situation here.
Exactly. So as a drone, or just as a multi-rotor aerial vehicle, we assume we have full control over the full range. So if you tell me, for example, I want the drone to have 6 numbers as the control input, I can always produce the 6 numbers from the 6 propellers I have. If you have, for example, a situation where you have only 4 propellers pointing upward, for example, like a quad rotor, and I tell the quad rotor to produce a force right or left, then you cannot produce this force. So that's the thing. So we have this under actuation. In this case, we have full actuation, so actual control becomes very easy. Always control of full actuated systems is the easiest thing. There's actually, it's like a side track. It's very, sometimes you can publish it, but it's like, usually it's solvable by itself. It's like very easy. When you have an underactivated system, it becomes very complicated, and this is where the research is about. Okay, you need to do really extra research. You need to think about, it's system dependent in this case. Yes.
So, as we can see, it's a different approach. Some different approaches that have different drawbacks. Usually here, is there any assumptions or drawbacks or things to consider before going to the Port-Hamiltonian for mechanical systems?
From a modeling perspective?
From modeling and then control.
From a modeling perspective, is this any different from the other equation we started with?
Fundamentally, no. The same factors.
That's it. So you come to class, you have a glasses on. You know, you have red glasses or you have blue glasses. Does it make a difference? I mean red, you know, shades. Does it make a difference? It's the same class, same information. You know, it's fundamentally the same stuff. The only difference is that, you know, if you have different glasses, you can see different stuff. So I can have a glass, you know, that has red, and I can see stuff, you know, better. Maybe then I have a glass that's maybe blue, or, you know, there's just, you know, metaphoric. You know, it's not practical. Okay.
This force, the direction of the arrows, does it refers to the flow of the bar from the source to the...
No. Flow of the power, that's a very good question. So flow of the power is always in the direction of the big arrow. You see this, so for example, when you say power, so when you say the arrow is like this, so we always assume that positive power, this is very important. This is just a convention for what is positive and what's negative power. So positive power is from the impedance to this Dirac structure, and positive power, okay, is into this C element or the storage element. And positive power is usually from the environment to the robot, not the other way around. What if you calculate this term and you find it's negative? What does that mean? It means that you have power being at this moment, okay? You have power going from the robot to the environment. This is just a convention. This idea of where the effort is going and where the flow is going is usually by this, what we call a causality stroke. So this is something I did not discuss. You see there's an extra bar here, you know, in all of these cases. Usually the bar tells you, this is just bond graph notation. The bar tells you this is the direction where effort is going. So for example, if this is the case, so here, and there's another convention that whenever we write a bond or a port, we have a half arrow, right? So we have one side with like a half arrow and the other side with no half arrow. Usually what's written on without the half arrow is the effort, and the other one is the flow. So here we say that effort is going here. So there's the impedance controller is telling what the wrench applied, what the control wrench is, while the drone is telling the impedance controller what its twist is. This is how you can read this, and so on. But more on that later, okay? We're going to be dealing on this part later. Yes. Yeah.
So since this is
this one or this one?
Yeah.
All of this.
No. It's just the particular.
This one. This one.
Yes.
Yeah.
So since the stroke is at the back, then that's the direction of the effort based on it.
Yes. So effort goes like this. But more on that later. This will become clear later, inshallah. Yes. Yes. Which one? The energy. Yes.